Welcome to Kushar Academy, Unleashing Potential. We are going to start part A of chapter 2, Work, Energy and Power. We'll be talking about what is work, what is energy and what is power. In this part of the tutorial, we are going to focus on work and power, and later on in the subsequent lessons we'll be talking about energy. The topics that we are going to cover is work, energy and power, and how are they related to force. Different types of energy, we'll be talking about it. Then how do we get energy, what are the energy sources, and principle of conservation of energy. So coming to force. Now we know that force can do many things. In the chapter 1 we have seen what is force capable of doing, like it can stop a moving object, it can move stationary object, it can change the shape and size. We are defining a new term here, work. So let's define what is work, and later on we will be understanding what are the implications of this definition. Work is said to be done only when the force applied on the body makes the body move. That is, there is a displacement of the body. It is saying that if we are applying a force and a body moves, that means it moves from one position to another position, we say that some work has been done. Now this work definition is a definition of physics, not the usual that we mean by work. For example, if you are solving a problem, a mental work is being done. That's what colloquial English means. But according to physics, no work is being done, because in physics what we have limited the scope to, that a force has to be applied and a displacement has to be done. When we are thinking of solving a problem, our brains are working in English, but there's no force and there's no displacement of our head. If that is so, work is not said to, it's said to be not done. There is zero work done in this scenario. So by this definition, measurement of work depends upon, first, how much force is applied, in which direction the force is applied, and second point, that the displacement it produces. Recall that displacement is the shortest path between point A and point B. Distance and displacement are different. Displacement is a vector quantity. The amount of work done by a force is equal to the product of the force and the displacement of the point of application of force in the direction of force. According to definition, if we apply a force here and the body moves from this position A to this position B, then since the two conditions are being met, what are those conditions? First, a force is applied. In a uniform motion where no force is applied, we will take up that as force is zero. So a body moves, displaces from A to B, the displacement is S, and under the influence of force F. So by our definition, work is force into displacement. Now recall here that if F is zero, that is, a body is moving by uniform velocity, that means by Newton's first law, there is no force. In that situation, this F is zero. In that situation, that means the work done is also zero. Second thing, if I am pushing a wall, I am pushing a big wall. No matter how much force do we apply, and if we are not able to move this wall, that means the wall is not getting displaced. In that scenario, this S is zero. In this case also, work will come to zero. In this example, say a ball A is dropped from a height h to the ground. The ball is at a height h from ground and it is dropped. So what are the forces acting on this ball? The force of gravity is acting on this ball, and force of gravity is weight of the ball, which is mg. This force is applicable till the ball A reaches point B. Ball reaches from A to B. So what is the displacement? This is the displacement h. What is the direction of motion? This one, downwards. So a ball displaces from A to B under the force of mg, and what is the displacement? it is H. So by our definition, what will be the work done in this scenario? Force into displacement. What is force? Force is in the downward direction, mg. And what is the displacement? Displacement is also in the downward direction. That means negative y direction. Force is also in a negative y direction. Direction motion is also in a negative y direction. So both are in the same direction. Hence, work done in this scenario will be mg force into displacement, that is h. So work done will be mgh. Now let's see this. The important point for the work done was force and displacement are in the same direction. That means the displacement has to be in the direction of force. Now just think that this is a block here and we are pushing it in the x-axis, that means towards east, this way. We know that in this, if we push a block in this direction, it will slowly move in this path. Continuously the force is being applied in this direction and the movement of the block is in this direction. So what will be the work done in this scenario? Recall that work done is force into displacement and displacement has to be in the direction of force. Now, what is the direction of force? Direction of force is in east direction. And what is the displacement direction? It is this direction. So, if we measure the x-axis, what is the displacement in x? If it reaches point C, it is this length, AB. And by trigonometry, we know that if this is the displacement S, AB will come as S cos theta if the angle of inclination is theta. So the displacement in the direction of force is this S cos theta AB. Hence, by our definition of work done, force into displacement will come as force and displacement in the direction of force, that is S cos theta. Hence, work done will be F into S cos theta. Now, for clarity, there is a question that a potter is moving horizontally and the load is in his head. So, what is the work done by the potter in moving the load? If we recall our definition properly, what was the definition? A force has to be present and a displacement has to be present on the direction of force. So, what is the force provided by this person to the luggage that he is applying? He is supporting it in the upward direction. The force of his head to support the load is on the upward direction and he is moving in the forward direction. That means his movement is perpendicular to the direction of force being applied. Same here, we can see the potter is moving and the force he is applying to support this load is on the upward direction and he is moving in this direction. So the angle is 90 degree. Force is upward direction, the displacement is perpendicular to it. So by work done is said to be F into displacement into cos theta. Here angle of displacement is 90 degree to the force. That means we have to find cos 90 degree. We know that cos 90 degree is 0. So the work done by the potter in supporting the load is 0. Similarly here, a person mowing a lawn. What is his direction of force? It is towards the rod, the handle that he is doing. And what is the motion of this lawn mower? It is this direction. So the displacement is, say, D. So again it will be F cos theta into D or Ft cos theta. A person standing still holding a suitcase. So if our question is, what is the work done by the person in holding a suitcase? We'll understand that person needs to apply a force to hold it against the gravity. If he doesn't apply a force, the suitcase will fall down. So he is working against gravity and applying a force of F. But is the suitcase moving? No. That means the displacement is 0. Since displacement is 0, the work done in lifting the suitcase or staying still with the suitcase is 0. This scenario is same as Potter moving the luggage on his head. This is what we are moving in our hand. To support this luggage, this suitcase, the force is applied on the upward direction and the motion of the suitcase is horizontal. So angle is 90 degree and cos 90 degree is 0. Hence the work done in moving the suitcase by the person is 0. This is also f cos theta and so on. Now suppose a body is moving in a circular motion due to gravity. The scenario can be a sun is in the center and earth is revolving around the sun. If I ask what is the work done by sun to make earth move? For this we'll have to consider a scenario. Suppose earth is here at this point. So the force of gravity, centripetal force that we have studied, is inwards. So the force applied due to gravity is inwards in this direction. What is the motion here? What is the velocity here? It is considered to be tangential at the point. Every point it is tangential. Suppose at this point the velocity is this way and the attractive force is this way. Again the angle is 90 degree. The work done will be f cos theta into displacement, but f into cos theta means cos 90, it comes to be 0. Hence the work done by the sun in revolving the moon due to attractive force of gravitation comes to 0. So we have to keep in mind, if the displacement is perpendicular to the application of force, the work done is 0. Again recapping the point, we'll find what are the conditions for the work done on the body to be 0. First, so the formula is given by F work done is equal to force into displacement. So either the displacement needs to be 0 or the force needs to be 0, or the displacement is normal to the angle of force. Cos theta, cos 90 is 0. Hence the work done is also 0. Now we'll discuss about work done by the force of gravity. Suppose there is a scenario, a box is in the ground and someone just applies a force for a brief moment of time and throws it above. That means the force is not constantly applied, just it is thrown up. So what will be the motion of this box? It will go at certain height and stop at the highest point of its path. Now in this scenario, we want to find out what is the work done by force of gravity. The displacement is this direction, top, or we can take it is in the positive y direction. We want to find the work done by the force of gravity. Gravity direction is always downwards, and how much is the gravity force? It is weight of the body or mass into g. So constantly the force applied on the body is mg in the downward direction. Initial velocity was in the upward direction and the force is in the downward direction. That's why the speed will decrease and at a certain point it will come to 0. Suppose this is the point where it comes to 0. So the direction of force is downwards, that means negative y-axis. The displacement is upward, that means positive y-axis. Hence the work done by the force of gravity will be force minus mg into plus h, because height is positive and the force is opposite to this direction. So work done by the gravity will be minus mgh. This is the same thing, or we can treat it as the direction of the displacement is above, the direction of force is down. So what is the angle between them? 180 degree. And if you apply that, work done is equal to force into displacement into, so if you write work is force into displacement is cos theta, so we will put cos theta as cos 180 degree, and value of cos 180 degree is minus 1. Hence the work done will be F into S into minus 1. F is our mg, S is h, mgh, into minus 1, we shall give it as minus mgh. So if the displacement is 180 degree opposite to the direction of force applied, work done is said to be negative. So work done is said to be negative. What are the other examples in which the work done is negative? Friction. Frictional force is always opposite to the direction of motion. That means if you are moving a box, the box motion is this. So friction direction will be this. Box comes. So if a box moves from point A to point B, the displacement is in this direction and force of friction is opposite 180 degree. Hence the work done by the friction is also always negative, and when the ball is thrown upward, the work done by force of gravity is also negative. Now since we have read so much about work, let's go to the units of work. SI unit of work is joules and it is abbreviated as J. Since work is given by force into displacement, force is Newton, displacement is meter. So 1 joule is actually 1 Newton meter. Going to the definition, how much is 1 joule? 1 joule of work is said to be done when the force of 1 Newton displaces a body through a distance of 1 meter in its own direction. If it is in the opposite direction, it will be minus 1 joule. That's why we are saying in its own direction. There are also bigger units like kilojoules and gigajoules. In joules, in a SI unit and CGS unit, 1 joule is 10 to the power 7 ergs. Like Newton is, if you want to convert from here, 1 Newton is 10 to the power 5 and meter is square. So 1 joules comes to 10 to the power 7 ergs. Now energy. What is energy? We know the definition. Energy of a body is its capacity to do work. If we have energy, then only we can apply force, and if we apply force and there is a displacement, a work is said to be done. So energy of a body is its capacity to do work. Whether it will be able to do work or not, we don't know, but its capacity to do work. Like work, energy is also scalar quantity. There are some different forms of energy that we calculate. One common unit is 1 watt hour. 1 watt hour means 1 watt into 1 hour. 1 watt is given as 1 joules per second into 1 hour is 3600 seconds. So 3600 joules is equal to 3.6 kilojoules. So 1 hour, watt hour comes to 3.6 kilojoules. Similarly, we can find out for 1 kilowatt hour. What it will write here? 1 kilowatt hour means 1000 watts for 1 hour. That means 3600 seconds. This gives us 3.6 into 10 to the power 6 joules. Smaller particles have smaller energies, so there are some smaller units also for energy. The atomic particle's energy is measured in electron volts. 1 electron volt is 1.6 into 10 to the power minus 19 joule. Common unit of energy is calories also. 1 calorie is equivalent to 4.18 joules. Remember, calorie is not in SI unit, joules is in SI unit, but earlier we used to use calorie for every type of energy, for we are converting calorie to joules. Now coming to power. What is power? The rate of doing work is power. Suppose this is an Olympic champion. He will be able to do this push-up much faster. Suppose this is a school champion. He will be able to push this but at a slower rate. So what is the work done for one push-up? The weight of the body and the displacement that we are doing here. A school champion also, if he is able to lift the weight, he also does the same work. But there is a difference. He is able to do faster and he is a bit slower than him. So there is some difference out of it. Work done is same, but faster or slower does matter also. So this quantity we measure how much work is being done at what pace, at what rate is known as power. So we define power as the rate of doing work. Power is also a scalar quantity and power is given by work done and how much time was it taken to do that work. That is, power is work done divided by time taken to do the work. Now, if you see, work done is force into displacement and power is work done by time. That means power can be written as force into displacement by time. But what is displacement by time? It is velocity or average velocity if we take t to be a longer period of time. So power can also be written as force into speed or average speed. So power is force into average speed. Suppose a force is applied in this direction and displacement in this direction. That means there is an angle theta between force and the direction of displacement. So work done in this scenario will be work is equal to Fs cos theta. Work done will be Fs cos theta. Power will be Fs cos theta by time, and S by T is V. That means F into V into cos theta. A scalar product is defined as F dot V, which gives Fv cos theta. This is the definition of scalar product. Another is work done also is given as scalar product in which force into displacement. That's why we write F into S into cos theta. This is a vector quantity and this is an operation of vector quantity which we will be seeing in the higher classes. For right now, we have to just remember Fv cos theta. Now, power spent by a source depends on two factors. How much work has it done and what is the time that he has taken. So, power is work done by time. So, if we define power, we say if 1 joule of work is done in 1 second, the power spent is said to be 1 watt. Watt is the SI unit of power. Watt in SI unit can also be written as joules per second. In MKS units, if you see what is the work, what is the unit of work? Work is defined as F into displacement, force is m into acceleration into displacement. So in MKS unit, the unit of work done will be, for m it will be kg, for acceleration it will be meter per second square into displacement, that means again meter. Hence meter means meter square per second square. In CGS unit, similarly, it will be the power, unit of power will be erg per second. What is the relationship between the SI and CGS unit? It will be 1 watt is 1 joule per second or 10 to the power 7 ergs per second.